Hello, I'm your host, Dr. David Urban, and I will be guiding you through Brown and Poon's Introduction to Organic Chemistry, 6th edition. The slides were downloaded from the Wiley Instructor Companion site and are copyrighted by Wiley. The commentary is my own. I have divided each chapter into smaller sections to make it easier to view on a wide variety of platforms. So let's begin. We will continue with Chapter 5, Part 4. Addition of water to alkenes. Okay, as we ended on the last video, we saw that Markovnikov's rule was a regioselective rule, but it followed those rules because of carbocation stability. The more stable carbocation yields the bond that will have the halide attached to it. Okay, so the regioselectivity is all about carbocation stability. If we form a primary carbocation, if we have the possibility of forming a primary carbocation versus a secondary or tertiary, we'll always form that secondary or tertiary first. Okay, let's see how that applies to the addition of water. Because remember, in the previous video, we saw that water follows Markovnikov's rule. Okay, so when we have acid-catalyzed hydrations of an alkene, we start with the idea that we have a protonated water is going to be added across that double bond. So in the case of something simple like propene, again, using Markovnikov's rule, we're going to add our hydrogen to the terminal carbon, and our OH is going to end up on our internal carbon, giving this 2-propanol as our primary product. Okay, as we go to other substituted materials like this one right here, notice we have a tri-substituted carbon here, meaning it's going to make a tertiary carbocation as part of its intermediate. That means we are going to, again, do a following of Markovnikov's rule, adding our hydrogen to this side and the OH to the more highly substituted carbon, or the one that would form the tertiary carbocation. Okay, so let's look at this mechanism step by step. The first thing we want to do is we want to protonate water. When we protonate water, that turns it into our Lewis acid. We have a hydrogen here willing to accept that electron pair from the alkene. Okay, so in this case here, both electrons from the double bond are going to reach out and grab that hydrogen to create a new sigma bond. And again, we want to generate the most stable carbocation possible. And in this case here, if we added the hydrogen to this side here, we'd make a primary carbocation. But if we add the hydrogen to this side here, we'll get a secondary carbocation. Now, that means we must add the hydrogen to the carbon that'll give us the secondary carbocation. So we're going to add it to this terminal carbon, and that's where this hydrogen goes right here. And we end up getting neutral water back, and we now have our carbocation. Okay, so that was our first step. So we went through our transition state of those electrons reaching out and grabbing that hydrogen, and we formed our intermediate here as our secondary carbocation. So the next thing that can happen is our carbocation can now act as an electrophile, or it can act as a Lewis acid and accept a pair of electrons from the Lewis base. And in this case, the Lewis base, or nucleophile, is water here because it has a lone pair for it to bond to. And so when it reaches out and grabs and forms that new sigma bond here, we end up with a charged species, this oxonium ion. Okay, so we're not quite done here, because typically these things are acid catalyzed, meaning that the proton that you add to the beginning of the reaction has to be recovered in the last step of the reaction. So let's think what the last step would be. It must be the taking away of that proton to regenerate our hydronium ion at the beginning. And so we have our water acting as our Lewis base, our hydrogen is our Lewis acid, and we generate our original hydronium ion that we had at the beginning of the reaction, and a neutral species here, our isopropyl alcohol. Okay. So let's look at a different substrate and see if we can generate different kind of reactions. Why can't we generate this product, but we can generate this product with this species here? Okay, so it all has to do with the idea that if there's only one hydrogen here and two hydrogens here, our hydrogen will always add to the side with more hydrogens, meaning our alcohol will always be on the more substituted carbon. Okay, so we'll always get secondary and tertiary alcohols from this and never form a primary alcohol, because we would have to form our primary carbocation. And since we don't form our primary carbocation, we cannot form our primary alcohol. Okay, so let's use that rule and figure out what the starting materials must have been from each of these. Okay, so if we had, like for number one here, if we had our double bond here, that could possibly make that product, or our double bond could have been here or here. Either way, the hydrogen would be going to the more substituted, the more hydrogen, the least substituted product, the one with more hydrogens on it. So our one could be this compound or this compound. Both would give a tertiary carbocation at this center, giving us our tertiary alcohol. So in the case of number B here, that means that our double bond could have been here or here. Either way, it's going to give us a tertiary carbocation here. So our part B could be this right here. Okay. Oh, it couldn't be that, because then we could get it here or here. Okay, because they would both give us tertiary carbocations, which means our double bond has to be somewhere else to make sure it doesn't show up in that other carbon. Our double bond has to be down here, so that we only get a tertiary carbocation and a secondary carbocation. So when we're deconstructing these things, we need to think about how can we get just one tertiary carbocation. Okay, so for part C, again, we would want to do it such that we have the double bond here or here, so that we could only generate a carbocation, a tertiary carbocation here. Ah, but that makes this one different. That makes this one different. So C, it's going to be where the double bond is in the ring here. But D has to be different. Let's look at D more specifically here. If we want the double bond, the tertiary carbocation, to be here, we can't have the double bond in between, because this would also give a tertiary carbocation. If this gives a tertiary carbocation, that means it can be in either one of these spaces. But if we have the double bond over here, it has to give, this is our tertiary double bond, so that this would only give our tertiary product. And actually, it looks like this molecule might be symmetrical, so we might get it either way. Okay, so now let's do something else. Instead of using water as our hydrating agent to add across the double bond, what if we added instead alcohol? So we still have an acidic proton there to actually work with it, but it's going to give us a different product, okay? So what we have here is, we're going to propose a mechanism for how we can take this compound here, the methanol here, and we're going to try to say how it would be equivalent to something like water right here in an acid-catalyzed system to give us this ether bond instead of an OH bond here, okay? So what I think is probably going to happen is we're probably going to protonate this alcohol just like we protonated the water. And then these, one of the hydrogens here is going to come and add to our double bond, giving us our tertiary carbocation. And then our tertiary carbocation is going to react with some kind of Lewis base, okay, to form our final product. So let's look at, oh, no, okay. So let's see how that can happen, okay. So we would have to draw it such that we have, let me give us a little more room here. Okay, so I think the first step of that mechanism is going to be generating a, let's see, OH, and we had a lone pair here, and if we added a hydrogen to it, that would create this acidic species. Then we can have these electrons reach out and grab that hydrogen, and that would generate our carbocation, our tertiary carbocation, CH3, 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 and a cation here. So now our cation is our Lewis base, and we've generated, because the proton came off, we have methanol again. So now methanol can act. Where'd it go? Oh, there it goes. Methanol can now act as our Lewis base. These electrons will go and attack that carbocation, giving us our intermediate, where we have a new carbon-oxygen-carbon bond. So that's going to give us an intermediate species with a hydrogen here and a plus charge. And when that plus charge goes away, we'll be left with our neutral ether species. We'll talk about that a little bit more in lecture. Okay, so now that we have a way of adding water and alcohols and HCl and HBr to that double bond, and it always follows that Markovnikov's rule that hydrogen adds first and then the other species add second. Let's look at the addition of chlorine and bromine to the double bond. It undergoes a slightly different mechanism, and we're going to engage that right now. So when we carry out these reagents, we typically do it in a solvent that we consider things that will not react with the halogens, like HBr and I mean bromine or chlorine right here. So we use what we call a halogenated solvent. A lot of times you'll see this as a solvent. It doesn't participate in the reaction, but it doesn't consume any of your starting materials either, okay? So whenever you see something like this under an arrow, that means it's a solvent. It just allows the reaction to happen, okay? So we have our double bond here, and if we have HBr, right, one's gonna go to one side and one's gonna go to the other side, okay? But we don't have HBr here, we have bromine. So we have a non-polar compound, it's bromine with all of its lone pairs around it. Have a sigma bond and lone pairs around that right here. So what's going to happen is we're going to take one of the bromines and add to one side and the other bromine and add to the other side stepwise to give us bromine on both carbons of the alkene, okay? So this is also a stereoselective reaction, okay? We typically only form one stereoisomer when we do this. And when we do this, we can actually see by using a cycloalkene that it only gives a trans product, meaning that bromine goes on one side of the ring and then it goes on the other side of the ring, which gives us what we call anti-stereoselectivity, meaning that one of the halides had to come from the top and one of the halides comes from the bottom because they're on opposite sides. They come on opposite sides are anti, so they're anti-stereoselective, okay? Now, so it's stereoselective, it's an addition reaction. We're adding one halide to each of them, and when we do it in a cycloalkene, we get only trans product. There must be a mechanistic reason for this, right? Okay, so let's think about this mechanism here, okay? So let's go back to what we have in our double bond here. We have those electrons, extra electrons in that pi bond, and they're going to react first, right? So in this case here, we have the electrons from the double bond reaching out to grab at one of the bromines. okay? When it does that, it uses its electrons to make a new sigma bond. When it does that, the electrons that were bonding the two bromines together with that sigma bond go to the other bromine, giving us bromide ion, okay? When it does that, we now have our partially positive, our carbocation here on the other one, and it can actually use the electrons on the bromine to make our new sigma bond here, and we actually end up with this bridge species called the bromonium ion, okay? So basically you have a bromine adding to the top of your double bond, giving you this three-membered ring and a positive charge, okay? This is important. This first step, this forming this bromonium ion ring, is what gives us our selectivity, okay? So if that forms now, and we have this positively charged carbon bromine compound, what has to happen next? The next thing that has to happen is our new nucleophile, our thing that's looking at for positive charges or things to share its electrons with, has to come in from the bottom of the species. The other bromine is occupying the top. All of our carbons are trigonal-planar, and so the bromine has to come from the other side of that. When it does, it comes and bonds to one or the other carbon. Doesn't matter which, but whichever one it does, it means that now this is on the bottom and this is on the top. And if it was the other way around, we would still have bottom and top. So it is an anti-addition. The bromines are coming in from the bottom to open up that ring to give us those in that configuration. And if we looked at that by a Newman projection, that would show the bromine is facing down on one carbon, but is facing up on the other carbon in that reaction state. Okay, so what that means is that it's when we do this reaction on this cyclohexane right here, we'll form bromine on the top right here, and then the other one comes on the bottom, giving us a single isomer. And when we make that isomer, as it forms, it originally forms as this trans-diaxial. But as we know, we want, whenever we have things on cyclohexanes, whenever possible, we want the two biggest groups to be equatorial. Okay, so it's going to flip a little bit and give us they're still going to be trans, but they're going to try to both be equatorial. Okay, so whenever we brominate a cycloalkene, we will typically end up with the trans-diequatorial product.